Lecture this morning will be given by Professor Etienne Ghys from the École Normale Supérieure de Lyon. He's speaking on From Chebyshev nets to Painlevé differential equations. Etienne.
Thank you, Paul. There will be essentially no new result in this talk. I just want to tell you a story of something that I liked recently, some kind of experience I had that makes mathematical life happier. So the story began a long time ago. I have been knowing Chebyshev. So I have been knowing this short summary of a paper of Chebyshev for years, maybe 25 years or something like that. In the collected papers of Chebyshev, there is this short page in which they explain that Chebyshev gave a talk in Paris in 1878, and that this talk was about cutting cloth. And the summary says that it was a very interesting talk, but unfortunately, the editors of the collected papers were not allowed to include the paper because it was not written on the manuscript print. So the editors did not feel like printing it. And you will see that somehow they were right, because it was just a draft, not a paper. Anyway, so for years I have been puzzled by that. What could be the content of this paper of Chebyshev? And 1.5 years ago, I was reading a PhD thesis in the history of mathematics dealing with something very different. And somewhere in a footnote, it was written that the author of the PhD had seen the manuscript. So I decided I wanted to see it. So I sent an email to this lady, and she told me that she remembered it was somewhere in Russia. That was really a challenge for me. So, and then fortunately I have a good friend of mine and a former student of mine who is Russian, and we decided to look for this paper. And it took us time, and finally in a box in the archives of the Academy of Sciences in St. Petersburg, we found it. It's a handwritten 35 or 40 pages long draft. Here's an example. It's written in French, sur la coupe des habits. It's written in good French, actually. And of course, when it took me time to get this manuscript, and the Academy of Sciences in St. Petersburg allowed the student to take a copy, but I'm not allowed to show it to you. For some reason, I'm not allowed to show it. Maybe it's a secret, top secret or something. I don't know. Anyway, it's explicitly mentioned that I should not show it in public. So please cut the television or something. So this is a wonderful paper. Containing a lot, I told you, it's very good French, but it's not good mathematics. There are many mistakes, computations, but it contains so many good ideas that I was really interested by that, and I wanted to understand it better, and if possible, to go further. So let me tell you the story. Fortunately, this was not completely lost. It was translated from French to Russian in 1932 by a Russian engineer whose name is Popov. And I have no idea it was widely circulated or not in Russia, but it was not totally lost. And some other reason why it was not lost is that Darboux was present during the talk of Chebyshev, and he wrote some nice comments about the talk of Chebyshev. So the content of the draft has not been lost. So you see it's really a draft. if I were an editor of the collected paper of somebody, it's unclear to me if you should publish that or not, because it was not intended to be published. And actually, I will tell you that what I did after that, and I wrote a paper that will appear in l'enseignement mathématique, and I suggested to l'enseignement mathématique to include at the end of my paper the transcript of this manuscript of Chebyshev. And the lady I mentioned to you complained because she said that Chebyshev would not have agreed. But I don't think so. I don't think so. So what is the paper about? The paper is about cutting cloth. So this is applied mathematics. You know, Chebyshev was really a fantastic mathematician, mixing all kinds of ideas from probability, from geometry, from approximation theory, from applied math, pure math. Everything was just a single thing. And according to what I saw somewhere, he was approached by the Russian army to optimize the cutting of uniforms. He was really involved in that, and then he went to what I'm going to tell you, and that he forgot about the contract with the militaries, and he did nothing with it. So the problem is this. You have a piece of cloth. The piece of cloth is made out of two families of threads, vertical and horizontal. I keep forgetting the English words for the first family, and the second, it's warp and woof. Woof and warp. Well, vertical and horizontal. Okay, so you have two families of threads, and they form little squares. And when you put this cloth on your elbow, for example, what's happening is that there's a deformation of the cloth, and the deformation, you can assume that the threads have constant length, but the angle between the threads is allowed to change. So when you have a little square, it is allowed to be deformed into a rhombus. So the practical question that you want to solve is this. You are given a shape, like, for example, an elbow, and the question is, how do you cut a piece of cloth so that you can apply it to the elbow without producing folds? So if you want to put that in mathematical terms, there is no fold. You will see. So here's the question. Let me put it in the mathematical terminology. You have a surface, and I call it clothable. If you can parameterize it by some open set in the plane, the open set being the piece of cloth, in such a way that the two vectors d phi dx and d phi dy are unitary, but you do not insist on having an angle which is 90 degrees. If you would insist on angle 90 degrees, that would mean that the surface is flat. And we know that most surfaces are not flat. So if we allow changing the angle, maybe we can clothe more surfaces. And this is the problem that Chebyshev is looking at. So let me tell you quickly why I am interested in that. Well, because we know we like Riemannian geometry in dimension 2. We have local coordinate system. Riemannian metric is written something like that. And we look for nice coordinates in which the metric is nicer. As you know, a nice coordinate, usually you have the concept of conformal coordinates. If you can assume that A is equal to C and B is equal to 0, and these are two equations, then you can solve it. I mean, you can have local isothermal coordinates for Riemannian metric in dimension 2. And the Chebyshev condition is just assuming that the two vectors have length 1, but you don't care about the angle. So there is no condition on B, but you have the condition that A is equal to 1 and C is equal to 1. So it's another way of finding a codimension 2 property in the space of Riemannian metrics. So it is not as nice, of course, as conformal structures, because there is no theory of holomorphic functions behind that. But anyway, it's a nice way of restricting coordinates in which the metric is nicer. That's my own motivation. So the theorem that one can find in Chebyshev draft, well, theorem in quotes, is that all surfaces are locally clothable, whatever the shape is. And the proof, if I can give you two proofs, proof number one is this. You just take on your surface two curves, a blue one and a red one. You declare that the blue one is one of the threads of the horizontal or the vertical family, and the red one, by definition, you force it to be on the horizontal family, and then you choose some kind of a mesh, like 5 millimeter, and with your compass, you complete the grid in such a way that all this grid is indeed formed of rhombuses. In this way, you get a discrete clothing, and you let these 5 centimeters go to 0, and you hope that they will converge to some smooth limit. And it is the case. You have to prove that. The second proof is much easier and much more comfortable. You take your hammock, and you install yourself in the hammock, and of course, the hammock will take the shape of your body. So there is a solution. Okay.
I cannot completely control the shape of your body.
Okay. Of course, the problem is that this is a local theorem. You see that in the hammock, because the hammock will get some, locally it's okay, but it will have some foldings, some singularities away from your body. So the theorem, the concrete theorem that Chebyshev proves is this. He shows that it is possible to clothe the sphere with two pieces of cloth. More precisely, he shows that it's possible to clothe a half sphere with one piece of cloth. So that if you take two copies of it, you clothe the full sphere. And in order to prove it, since Chebyshev was really an applied mathematician, he does it. And in the box in the Academy of Sciences in St. Petersburg, not only you have the draft, but you have the following object. This has been cut by Chebyshev himself. And this is the handwriting of Chebyshev. So his contribution is this. If you take a cloth and if you cut the cloth on this shape, and if you put it on a ball, putting the center on the North Pole, he claims that this piece of cloth will just cover the northern hemisphere, and the boundary will go to the equator, and there will be no fold. This is the theorem of Chebyshev. Actually, you will see that I will explain that to you later, his proof is more approximation than real. It's not really a proof, anyway. So what I want to do, because I have 130 years in advance from Chebyshev, I can do better than him. So here's what I want to do. I want to show you how it's possible to clothe the sphere with only one piece of cloth. Let me show it to you. Here's the thing. This is the main picture of my talk. So I claim that if you cut a piece of cloth in this star-shaped shape, if you put the middle point on the North Pole and the four corners on the South Pole, this will cover exactly the sphere minus 4 arcs. I will show that you better in a moment. So on this picture, I did not draw the threads. The threads are just horizontal and vertical lines. What I did draw in blue, these circular curves in blue, are the curves which are mapped by the clothing on parallels of the sphere. And what I did draw in red are the curves which are mapped by the clothing to longitudes.
So the blue one goes to the equator?
So, and the thick one, the thick blue one, let's call that the Chebyshev line, is the one which is going to the equator. So if you cut this not along the yellow boundary, but along the thick blue one, you get the previous Chebyshev picture. So Chebyshev was not courageous enough to go far enough to go to the South Pole. He stopped at the equator.
Yeah, but what's the interest for closing to do that?
One second. What?
I mean, on the closing point of view, you can understand that you want to do half a sphere, but the complete sphere, you are not going to put that on.
Why not?
Assuming that the machine which does it,
Why not?
the machine has to be on both sides of the piece, and then you cannot,
Why not?
destroy the
Okay.
destroy the piece of paper.
Don't destroy my talk. Okay, so let me show you that in practice. And since I like producing motion pictures, let me show you that in practice. So here's the piece of cloth, and then I'm going to cover the ball. So the ball is coming, and the four corners will wrap. Let's see. So Charles, do you like that? Can I get a patent for that? Yes, I can.
No, it's perfectly in Europe. It has been published for some time, so you can
Okay, so you see.
do that 1 year after publication.
Okay, so you see the main point is that all these little quadrilaterals are rhombuses. Okay, now I want to show you how it is possible to prove that. I mean, that it's possible to do it such a thing. Well, I should mention two theorems which are related to that and rather recent, like 2001 and 2003 or something like that. So Bakerman and Samuelson, no, this is 1995 or something. They did prove in the rigorous modern mathematics, they did prove the theorem of Chebyshev. They did prove that the half sphere can be closed. And more recently, and this is, I think, 21st century, Burago, Ivanov, and Malev proved the following theorem, that if you take a simply connected surface whose amount of positive curvature is less than 2 pi, and whose amount of negative curvature is also less than 2 pi, then you can close it. For example, a half sphere. I remind you that the total amount of curvature on the sphere is 4 pi. So this theorem is nice, but it's not going to the South Pole. Okay? It's just half of the sphere. How does one construct such clothings? I'm not going to write too many formulas. I just want to give you the key ideas. Suppose you have a clothing, phi. So from the plane to the surface. And you write the second derivative, d2 phi dx dy. You write it as d dy of d phi dx or d dx d phi dy. Then, by definition, you remember that d phi dx has norm 1. The derivative of a vector of norm 1 is orthogonal to itself, to the vector. So this second derivative, this mixed derivative, is orthogonal to d phi dx and orthogonal to d phi dy. Hence, is orthogonal to the surface. And this is the key point. The clothing is just a map phi such that the second derivative, d2 phi dx dy, is everywhere perpendicular to the surface. If you can manage that, you have a clothing. Now, if you have that, you deduce that if you take the vector field d phi dx, which is tangent to the threads, well, this vector field is parallel along the other curves because derivative is perpendicular to the surface. So what you have is you have this surface with two families of curves. They are not geodesics, but the tangents to the first family are parallel along the second family. And the tangents to the second family are parallel along the first family. If you use that, you can easily compute the geodesic curvatures of the threads. You know, to compute geodesic curvature of a curve, you take tangent vector, you move along the curve, and you compute the amount of rotation. So easily you get that the geodesic curvature of the x curves is just the derivative d omega dx, where omega is the angle between the threads. So you get a nice formula for computing curvatures of the threads. For example, if you have two threads which are perpendicular everywhere, or if the angle is constant along the threads, then this is geodesic. This is explicitly mentioned in the draft of Chebyshev. So you compute easily the geodesic curvatures of the two threads. And from that, you can easily compute the Gauss-Bonnet formula. How do you compute, how do you compute Gauss-Bonnet formula? You have on the left-hand side, you have the Gauss-Bonnet integral. So this is curvature, or this is KUV, should be KXY, sorry. So you have the integral of curvature on a rectangle, limited by two threads, by four threads, two horizontal, two vertical. And here on the right-hand side, I say that the integral of curvature is nothing more than the alternating sum of the angles at the four corners. Why is it so? Well, this is, this is the famous picture. How do you compute integral of curvature on a domain where you look on the boundary and you parallel transport a vector? But we know geodesic curvature of the boundary because I gave the formula for you. I promise, it's a very simple exercise. You get this, and this is called the Hasidaki formula. If you take an infinitesimal rectangle, the previous formula gives you the formula for the Gaussian curvature of a closed surface. Gaussian curvature K is given by this mixed derivative d2 omega dx dy. We have this nice formula. Okay, now we want to close. This formula is in Chebyshev. Now you want to close with a mistake. It changes sign. Okay, now you want to close the sphere. The sphere has curvature +1. So you put +1 in this formula, and you get a nice PDE. And this PDE is a very famous PDE in mathematics. It's the Sine-Gordon partial differential equation. It's one of the most famous completely integrable partial differential equation. It has been introduced when?
Yankee.
When was that?
Sophus Lee was first.
Sophus Lee?
Transferred Yankee transformation.
So how does that compare with Chebyshev?
1980 he proved, but it was not for that problem. It was negative curvature.
Okay, I'm going to do that now. Okay.
Sophus Lee, yes.
Okay. But that was after Chebyshev?
I think it was independent. I even didn't know that for Chebyshev nets.
Aha, okay. So to remind you quickly why this is important for physics, I'm not going to give you a course on this kind of PDE, but this is, you take a series of pendulum connected by springs like that, and each one interacts with the next two ones, and you have an equation for this motion, and when you go to the limit of little infinitesimal springs, the limiting differential equation that you get is precisely the Sine-Gordon PDE. So this is really famous for the existence of solitons, and this is wonderful physics and wonderful mathematics. And this is the same. You have to replace, this is the two ways of writing the wave equation. But this is the same equation, basically. Okay.
Excuse me, but in this case, there is a difference from Sophus Lee here, because Sophus Lee transferred into Sine-Gordon terminology already, I would say, indication to complete integration.
I see.
And here is only derivation of equation.
Okay, of course. You're sure. Anyway, so what Chebyshev is doing in front of this PDE is that he's looking for a solution. So he looks for a simple solution, and he looks for a solution omega as a function of the product xy. So you look for omega xy as a function u of xy. And then you replace this PDE by an ODE. Yes?
So the point between x and y on the first line and in the omega is a comma or is a comma?
It's a comma. It should be comma. Is it a comma? Well, on my screen it's a comma. On my screen it's a comma. Okay. Okay. So it's a function of two variables, and you put inside your differential equation you put a function of one variable, and you look for u of xy. So your PDE turns into an ODE, and this ODE is this one. And this ODE is written in Chebyshev. And what Chebyshev does is that he looks for a solution, but since he's doing applied mathematics, he just takes this and stops there. He looks for a solution up to the third order, and the picture I have shown to you that this template for clothing the sphere is constructed using that, nothing more than that. It doesn't go further. Of course, if you want to go further, you can use this computer, and you get this function. And if you use a little bit of my brain, you can prove that there is indeed a solution which is defined for, which is real analytic and which is defined for all x, etc., etc. And this is a picture of the graph of this function u. So you have this function u. And now you play the following game. You construct the Riemannian metric in the plane given by this formula. It's dx squared plus dy squared. No choice because I want a Chebyshev net. And in the middle I put 2 plus 2 cosine u of xy dx dy. This is a Riemannian metric in the plane, except that it might be degenerate in some points. When the function u achieves the value pi or multiple of pi, this Riemannian metric is degenerate. But anyway, in the plane, in the full plane, you have a real analytic, beautiful field of quadratic forms, which is non-degenerate away from a finite or countable family of hyperbolas, and you have a nice Riemannian metric in the complement of these hyperbolas. And by definition, the curvature of this metric is +1. Because the function u has been chosen exactly for this purpose, has been constructed because I wanted curvature 1. So this metric in the plane has curvature 1, except that it's not a metric. It's degenerate on some lines. Then, well, what you do is you take the, let's say, exponential function. And this is the point I'm not going to prove today. This is the hardest part of the proof. You prove that there is a unique isometry, psi, going from the full plane, R2, to the full sphere, S2, and which is an isometry between the plane and the sphere. Except that, of course, the word isometry between plane and sphere is provocative. But it's what's happening is this. This is an isometry, except that this map phi, of course, is real analytic. Its differential at some point is not onto. But at those points where the differential is not onto, the metric is degenerate. So if you take a tangent vector to R2, take its image by the differential of phi, these two vectors have the same length. If you measure the length on the right on the sphere, and on the left on the plane with this metric. So really, this is an isometry between a plane and a sphere. Except that the plane is equipped with this metric, which is somewhere not degenerate, singular, or degenerate. And then you have this isometry, and this is global. This is a very explicit map from the plane to the sphere. And what you have to do now is you have to cut, and this is, I'm not going to explain that. You have to prove that if you cut in the plane a suitable domain, and this suitable domain is precisely the asteroid shape I showed you, when you restrict this isometry to this suitable domain, the restriction to this domain is onto. the sphere. And this is unfortunately kind of messy. I'll prove it, but I'm not showing that to you because I'm not proud of the proof. It's kind of a dirty proof. It's not nice. It's not a covering space. Okay? It's not one-to-one. It's infinite degree. So asymptotic degree is infinite. If you restrict it to big ball, it will cover the sphere many times. It's like I'd like to understand it better. The picture I showed you shows you the picture in a small neighborhood of the origin. But if you go further, you see waves of some kind of solitone. So it's a kind of it's a nice map.
And the places where the differential is non-surjective is like there are a bunch of curves like these asteroids, or?
No, the place where the differential is not surjective is the union of hyperbolas. So let me show you this is a local picture to show you. So you have in black the hyperbola. And in blue, you see the curve which is mapped to longitude. And you see that the blue curve this is 1/4 of the asteroid I showed you. So I'm not saying that the boundary of my asteroid is in the singular locus. The boundary of the asteroid is not made out of hyperbolas. It's a very complicated transcendental curve, and this boundary touches the hyperbola only in one point. If we speak of, in the terminology of Tom or whatever, the map phi has France. No, what's France, cuspidal point. Yeah. So there is the map phi has a cuspidal point right in the middle in this middle point. Okay. So really, this is not a conformal map. This is a nice picture. Anyway. Okay. So I have to tell you that I was very ashamed, because it took me a long time before I realized that this ODE that I discussed, a second order ODE, was very familiar to me. But I didn't see it with the right glasses. And I was ashamed that it took me so long before I realized that something that many people knew, that one can transform this ODE in some other famous ODE, which is one of the Painlevé differential equations. If you change variable and you put w exponential of minus iu, then the ODE with sign becomes this rational differential equation, which looks complicated, but which is rational, which is not transcendental anymore. There's no more sign. And this is a special case of one of the Painlevé differential equations. Let me remind you very quickly that at the beginning of the 20th century, Painlevé was looking at these differential equations of the second order in the complex domain. And for him, it looked like a huge quantity of differential equations with no clear idea of where to go. I mean, what kind of equation should we select? Which equations are more interesting than others? R is a rational function. And what Painlevé suggested is to impose a condition, which is called now the Painlevé property, that all movable singularities in the complex domain are poles. I'm not going to go into many details. But with this additional property, Painlevé proved this incredible, fantastic theorem that if you impose this simple property, you have only 6 possibilities for the differential equations. And at the time, and this is the third one, it depends on parameters alpha, beta, gamma, and if you choose properly the parameters, you find this Chebyshev differential equation I mentioned. And what?
Self-similar solutions of completely integrable
Yes.
normally linked to Painlevé. And is it some sort of self-similar solutions for sine order?
For this one?
This one.
Yes, yes, it is. Yeah. And what happened, just a word of history, that this is an example where I think Poincaré made a big mistake. When Poincaré saw this theorem of Painlevé saying that the only 6 differential equations have this property, Poincaré said to Painlevé, your equations are like 6 islands in the middle of a huge continent, a huge ocean. So he was convinced that they were just like, little things not connected to the main continent. But he was wrong. I mean, today we know that these partial differential equations, these ordinary differential equations, appear everywhere in mathematics and appear everywhere in physics. That was a big mistake of Poincaré. Yeah, this is what I wanted to say. There is some kind of conjecture or whatever. I put it in quotes because it's not well defined. That there should be some kind of connection between complete integrability for evolution PDE and the Painlevé property and Painlevé differential equation. So it's not kind of a big surprise that the Korteweg-De Vries equation, the Sine-Gordon equation I mentioned, is connected with Painlevé is not a surprise today. Okay, anyway, so for me it was interesting because I like to generalize from real to complex and to holomorphic. And since I discovered that the Painlevé properties, the Painlevé functions exist in the complex domain, well, I'm happy because now I can complexify everything in the previous picture, and I get a meromorphic metric on C2, which has curvature +1. And this, I can even complexify the clothing I mentioned to you. This map from R2 to 2 sphere is actually the restriction to the real plane of a meromorphic function from the complex plane, C2, to the complex sphere, which is the complex quadric. And even you can do better, you can even find a holomorphic clothing of the product of 2 projective lines by C2. But this holomorphic clothing is transcendental. It's meromorphic. It is far from being algebraic. I think it's a nice geometric object. Okay, so a simple remark, of course, is that you want to change sign. We had the PDE with d2 omega dx dy is minus sine omega. Let's go to curvature -1. Instead of clothing the sphere, I now want to close the hyperbolic plane, the Poincaré disk. And indeed, you use the same function u, the same equations, blah, 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 and you get the following picture. This is a piece of cloth limited by 2 hyperbolas, and you vaguely see in red the curves that will be mapped by the clothing onto radial geodesics in the Poincaré disk. And here's the clothing of the Poincaré disk. So you see here a part of the Poincaré disk, which is limited by these 4 curves, which are not geodesics. And you see inside the clothing. And you see on the boundary that the threads become tangent. So somehow this boundary is some kind of maximal domain of existence of the clothing. Okay? So you have this clothing of Poincaré disk, and what I like in this clothing is that the area of this domain is infinite. So it's a clothing of an infinite area chunk of the Poincaré disk. So what can you do with that? Well, we can do something that I think Chebyshev did not see for many reasons, and that Hilbert noticed later. Hilbert noticed that the problem that Chebyshev was discussing was directly related to another fundamental question, the question of isometric embeddings of surfaces of curvature -1 in 3 space. you have here the picture of the pseudosphere. You know, it's an attempt of finding a surface with curvature -1 in 3 sphere. And it's well known that if you try to extend it as much as possible, you run into trouble because you have these kind of lines of singularity. If you try to change the situation, you get these Dini surfaces having this, again, this line of singularities. So it was a very old question of knowing if it's possible to embed isometrically the Poincare disk in Euclidean space. And Hilbert proved that it is not possible, and his main tool is indeed to connect that with clothing. Hilbert noticed the following. He noticed that if you take a surface with curvature -1 in 3 space, and if you look at the 2 families of asymptotic lines on this surface, then these 2 families will define a clothing for you. And conversely, if you give me a clothing, you can construct an embedding or immersion of the surface with curvature -1. There's perfect dictionary between clothing in the sense of Chebyshev and isometric embeddings in the modern sense. And what also Hilbert noticed, it's not clear that he noticed it, but anyway, this is easy to see, that if you take a surface with curvature -1, if you can take a Gauss map sending the surface to the sphere, the Gauss map will send the asymptotic lines to a clothing of the sphere. And conversely, if you give me a clothing of the sphere, you can think of that as being the Gauss map of some embedding of the Poincare disk. So this is really a beautiful dictionary between all these objects. And for example, the 2 objects I showed to you, the clothing of the sphere with the 4 corners, and the clothing of hyperbolic disk with these asteroid shapes, they are related by the Gauss map. I intended to show you the proof of Hilbert's proposition, but I was taught when I was a student that no talk should contain no proof. So, so I said to myself, well, let me prove them. I wanted to prove that, but since time is going fast, I'm sorry, I will drop the proof just to show you it's computations. Okay. Anyway, this is the proof of Hilbert. This is a very clever proof. And Hilbert deduced from this fact that there is no embedding of the full disk in 3 space. And his proof is now 2 lines. If there were an embedding of the full disk in 3 space, there would be a clothing of the full disk. And then you would apply Hasidakis' formula to a big rectangle, and this formula will tell you that the integral of curvature of this rectangle, which is the area of this rectangle, is the alternating sum of the angles. But since the angles are between 0 and pi, the alternating sum is at most 2 pi. So any rectangle has an area less than 2 pi. So it's not possible to clothe the full Poincare disk. That's the proof of Hilbert. You know, Hilbert is fantastic. Now, since I told you there is a dictionary between clothing and embeddings, since I showed to you this clothing of a part of Poincare disk, this should produce an embedding of a part of Poincare disk in 3 space. Here it is. Here's a surface with four ends, limited by 4 curves. We will see it better in a moment. And this interesting story too. 2 months ago, I was convinced that I was the first one who discovered this. And I was happy with this nice surface. And then I discovered, 2 months ago, but less than 2 months ago, that this surface had been constructed by Amsler in 1955. And I don't know why. I mean, maybe when I was younger, you know, you prove a theorem and then you discover that somebody else did it before. This is something that happened to all of us. But when I was younger, it was like a terrible experience. But now, I was happy. I think it's something new that for me. It's something that I think it's good. It's good to feel part of a historical motion. I mean, it's good to. It's called aging. Yeah, exactly. This is exactly what I mean. It's a pleasure to discover that I have some contact with this guy in 1955. Yeah, I like that. So this is Amsler surface. So let me show you a few pictures of that and a film. So I'm going to show you Amsler surface, which is obtained by clothing this part limited by two hyperbolas. I will show it to you. I will pick a point on it, sliced by the tangent plane, so you can see that indeed the asymptotic lines are the threads. So this is the Amsler surface. That my wife called it torticoli. So you see the boundary curves are points where, you know, the metric degenerates because the asymptotic lines become tangent. So you pick a point on the surface, take the normal, take the tangent plane, and you will see the tangent plane indeed intersects the surface along the asymptotic lines. Now, it happens that I have a good friend in Lyon who is an artist. He's not a mathematician, but he likes mathematics. And I met him and I told him about this clothing of spheres, etc., etc. And he was enthusiastic with that. And let me forget about meromorphic thing. And he was enthusiastic, and he said to me, well, you're a mathematician, you prove theorem, I want to do it. I want to construct it with my hands. So he wanted to construct this clothing. So first of all, he tried with this kind of, this wire metallic thing, and it was not convincing at all. So he decided to build it in wood. So here's the trick. You take a board, and then you cut circular rings, and you collect them, you glue them. You know, it's a huge amount of work. And then you have to smooth it. And then he asked me to send him the coordinates, point by point, of the threads. So I sent him an Excel file, because he knows how to use Excel. So I sent him the coordinates, longitude and latitude of each point, and then he began drawing the threads on the board, and then he wanted to put some metal in it. So, you know, that's a lot of work, you can imagine that. And that's almost finished, but this is not finished. This is big like that. And then it was really interesting for me because, you know, this guy is very clever. He told me, Etienne, good, you can cloth a ball, but okay. Can you please, for me, could you cloth an ellipsoid? And then I said, I don't know. And still today, I don't know. So let me explain to you what I can do. I have a partial result. And let me make some kind of conjecture or some kind of... here's the thing. So you are given a surface like a convex egg, and you want to close it. So let me give you a theorem I can prove. Well, the theorem is this. You take a compact surface, Riemannian surface, and on this surface you take two geodesics. You suppose these two geodesics intersect at the origin, of the gamma 1 of 0 is gamma 2 of 0, and they intersect transversally. Then the theorem is that there exists a global clothing in quotes, I will explain that in a moment, there's a global map phi from R2 to the surface that maps the coordinates, the axes, to the geodesics, and which is a clothing in the weak sense that along verticals and horizontals, it is isometry. But it is not, I'm not saying that phi is onto. It is a map from the plane to the surface, restricting to horizontal vertical, it's isometric. The differential of phi might be singular at some point, like in the case of the sphere, but I did not say that the map is onto. There might be some areas on the egg which are not covered. Well, this is not a difficult theorem. It's kind of a standard application of hyperbolic partial differential equations. You have to measure you have to extend it to infinity, so it's some kind of completeness of a hyperbolic PDE, but that's not very difficult. But the corollary of that is that if the convex surface is almost a sphere, if the curvature is almost constant, then you can cover it. You can clothe it. And the proof is that since the map is onto for the sphere, when you change a little bit the shape of the egg, the map will continue to be onto. And so after this small deformation, it is still possible to cut a suitable template in the plane in such a way that the template covers the full deformed sphere. So indeed, I can prove local theorem, which does not satisfy at all my friend. Because he said, well, how much of curvature are you allowed to change? This is just a local. There is this epsilon such that. I have no idea. So really, this is the best I can do. So here's to show you what the kind of PDE you have to solve. This is the PDE that you have to solve if you want to clothe. And the gamma, I, j, k are the Christoffel symbols. And this is not hard to do, but to see if the map is onto is almost impossible for me, at least. So here's, for example, a computer simulation. If you take an ellipsoid with axes 3, 4, 5, you clothe it by the map I mentioned. This gives you a map from R2 to the ellipsoid. At each point xy, you have an angle. And here, this is the numerical value of cosine of omega as a function of xy. So it's kind of a bumpy function. It's unclear to me what's happening. I have no idea if this map might avoid a little tiny hole in the ellipsoid. I have no idea. One way to one hope I have would be to use the elliptic coordinates for the ellipsoids, and I would like to use the Painlevé 3 equations. Maybe I can clothe it holomorphically. That would not make my friend happy anyway, but this is the thing I'd like to do. Okay, so let me finish by mentioning one or two things about my friend. So he's doing, he's not a mathematician, he's an artist, I told you, and he loves mathematics. And I think it's interesting that there are mathematicians who are not receiving money for doing mathematics. They love math. You know, you meet this guy, I like your theorem, I want to do it, and he goes, you know, building a ball and trying to understand and reading my paper and asking me hundreds of questions about how to do it. It's something we should not forget. When there are non-professional mathematicians, we have to communicate with them. This is something really important. And let me show you the kind of clothing that he's interested in. So Pierre is interested also in geodesics on surfaces. And recently in Lyon, he had an exhibition that I liked very much. Unfortunately, I was almost the only one to like it. The exhibition was called Imaginer, which I think was a good title. Okay, thank you very much.